All right, a very warm welcome to our IAU Local Universe seminar. My name is Matthias Steinmetz. I'm the Vice President of the Commission, and our President is also present today, but she is also presenting, and therefore she has asked me to chair today's meeting. The meeting is recorded. We have two talks, and let me just give you a bit of netiquette for the meeting so that everything works smoothly afterwards. So during the talks, please mute your microphone so that we are undisturbed from every background noises and so on. It's always nice to the speaker if a few people of you leave their camera on, that you actually talk to live people and not just to a camera. After the talk, we have the first talk will be 25 minutes plus 15 minutes discussion. The second talk will be 12 minutes plus 8. If you want to participate in the discussion, my proposal is to do that via the chat. So just put a little word in the chat that you have a question, and then I give you the word. Or if your connection is bad, just type your question into the chat and I will read it for you. Whatever works best for you. I think that would be it for the introduction, and I would like our first speaker, that's Kayati Malan. He's currently a postdoc at the Max Planck Institute for Astronomy in Heidelberg as a Humboldt Fellow working with Hans-Walter Rix, and he will talk on the Global Dynamical Atlas of Milky Way mergers using ESA Gaia dataset. And I give you the floor and ask you to share your presentation.
Hello, could you please confirm if you can hear me well and also see the slide in the full screen?
We see you well and we hear you well.
Perfect. Hello, everyone. It's a real pleasure to be talking to all of you today. So I'll be talking about the Global Dynamical Atlas of Milky Way mergers. So the broad question that I will be addressing is, how did the Milky Way galaxy form? Or more specifically, how did the stellar halo of the Milky Way galaxy form? And in this regard, I understand that all of us mostly understand that the Milky Way halo formed by the merging of small foreign galaxies that fell into the galaxy, got disrupted and populated the stellar halo. So I will be talking about those lines, but more specifically, I'll be talking about some new results that me and my team have received by processing the excellent Gaia data using some of the state-of-the-art algorithms. And in this regard, I firmly believe that developing high computational tools and building state-of-the-art algorithms is one of the good ways to go about exploring and trying to understand this rather complicated but yet beautiful data set of Gaia that we have. So before proceeding further, this video that you're seeing is of the Milky Way, but primarily I want to highlight these streams that you're seeing. So these are the streams that we have detected with Gaia DR2 and EDR3 using the Stream Finder software. So I'll be talking a bit about the Stream Finder software as well. And this movie is basically 2 days old, so it's giving its first public appearance right now. So yeah. So now proceeding forward, the general question, the broad question that we are trying to understand is, how do Milky Way mass halos form in our universe that is dominated by dark matter? And we know that the lambda CDM makes this very strong prediction that the Milky Way mass halos formed by accretion and merging of numerous dark matter subhalos. Of course, if you have baryonic simulations with baryons, then those can be interpreted as galaxies and not just dark matter subhalos. And of course, this is not the only prediction that lambda CDM gives. It gives details about the mass function of those accretions. It gives us details about the rate of accretion. So for example, it suggests that the rate of accretion was very high at high redshifts, more than 1.5 redshift. And that the accretion has become rather passive and stationary in the more recent times, in the last 5 or 6 gigayears ago. So we get these predictions from these simulations, from the theory. And now what we want to do is we want to contrast this theory against the observations that we have received from different data sets. And then again, for the past 20 years or more, we've now realized this, and we have come to this conclusion that indeed the Milky Way halo was formed by the merging of these galaxies that fell into our galaxy and then got disrupted. And this conclusion we have reached in part based on several surveys that indicate that the halo is not smooth, but it's highly structured. And this we've seen with different data sets at different times. So we know that the halo is structured because we have detected the Sagittarius stream, we have detected the Helmi stream, we have digged into the SDSS, processed it, and realized that the halo is very structured. We know of the Cetus stream, and then the more recently, the Gaia sausage Enceladus structure. So we have seen these evidences in different ways. However, the challenging question still remain is, for example, what are the total number of mergers? Are there 5 mergers or 10 mergers or 20 mergers? So it's in reality, it's an open question. And then what were the initial properties of these mergers? What were their stellar mass, their dark matter halo mass, their metallicities? This is also in a way an open-ended question. The new question that you can think of is that, as I showed you, that the Milky Way halo harbors a large population of globular clusters, satellite galaxies, and streams. So you can ask that which of these halo objects came inside which merger galaxy. So we generally talk about just stars, but you can also talk about which clusters or streams or satellite galaxies came inside which merger. And of course, answer to these questions are important to inform the galaxy formation models and then improve them or rectify them if needed. So this brings me to the outline of the talk. So I'll be talking about some of the work that I've been doing with my collaborators in this direction of trying to understand the formation history of the Milky Way halo. And specifically, I'll be focusing on the detection and analysis of the Milky Way mergers by processing the Gaia dataset using some of these algorithms. So specifically, I'll be talking about 2 algorithms. The first one is Stream Finder, which is an algorithm to detect stellar streams of the Milky Way. And then the next one is a combination of the NLink algorithm plus some statistics, which basically provides you a new technique to detect the mergers in the action space. And admittedly, now is the best time to do this because with Gaia, we have excellent proper motion. So this additional kinematic information allows us to disentangle the kinematic features from the field stars that we have in the galaxy and then try to understand, unveil different mergers in the Milky Way and try and understand how our galaxy was built. So now I'm moving to the first part of this talk, where I'll specifically talk about the stellar streams, which are the probes of the Milky Way halo. And this is because the stellar streams, by the virtue of their formation, serve as the testimony of the hierarchical formation of the Milky Way. Because if you have a small merging galaxy that accretes into the galaxy, in most of the cases, if the disruption is rather slow, the galaxy would end up forming a stream. So just if you have a detection of a stream, or just if you can find a stream in a galaxy, not just in Milky Way, in any other galaxy in the universe, you'll say, aha, that the halo must have built, at least some part of the halo would have been built by this accretion process. And then, of course, streams provide an excellent opportunity to constrain the number of mergers, because in principle, you can just count the number of streams, and that can put a lower limit on the number of mergers in the Milky Way. Of course, this is true for the broad dwarf galaxy streams. And because streams closely delineate orbits, as you can see in this movie, you can also try to construct the distribution function of these mergers, because you can trace orbits backward in time along the streams and then try to construct how these different mergers fell into the Milky Way along which orbits. So this was the question that I was faced with in 2016 when I was doing my PhD, when I kind of started my PhD. And the question that I was given was that, what is the best way to detect streams using Gaia DR2? So DR2 was still to come in April 2018, and I had to prepare for it for about 2 years or so. To basically try and find a technique with which we can detect streams in the Gaia dataset. So we came up with this algorithm that we named Stream Finder. So what Stream Finder is doing is that it's finding streams, as simple as that. What it does is that it takes the input as the Gaia dataset. So it takes the 2D positions, the parallaxes, the proper motions, and then the photometry, and then the uncertainties associated with these measurements. It processes the Gaia data. So what it does is that for every star in the data, it samples orbits. And it samples orbits consistent with the observed kinematics and photometry of the stars. So you try to count for stars along the integrated orbits, and the star that has more friends along the orbit is likely to be a stream star, and the star that has less or zero stars is basically a contaminant. So that's the general broad idea of stream finder. And stream finder can be summed into the single equation. It's a complicated algorithm, but it can sum into this equation where you have a model term and then you have a contamination term, and the contamination model is built using the Gaia data itself. And then the output is basically you get this map of stars, of Gaia stars, and in this map, each star is a Gaia source. And you can see that at a given some significance threshold you can make. So this is an 8 sigma threshold detection. So you can see all of these star streams that we are seeing here are 8 sigma detections. And then you can see these streamy features. So here each star is color coded according to its proper motion along the latitude direction that shows you that these structures that we are seeing are also coherent in the kinematic space. So we can focus a bit more on this map, and then it basically shows you the disruption of different progenitors. So I can focus on some of these streams. So there's this famous GD1 stream, which is about 100 degree long. Then you have the Silger stream, which has a metallicity of -2.92. So it's very metal poor stream. Then we have the stream of Fimbulthal stream, which is the stream of the massive globular cluster omega sen. And then there's these different streams that are associated with globular clusters, and some streams of which are progenitorless. We do not know the nature of their progenitors. I would specifically want to point out this very recent result, the C19 stream. And I think it's fair to say that it happens to be the most metal poor substructure of the universe. So we find, so this C19 stream that we detected using Stream Finder in Gaia EDR3, it has a metallicity of -3.38 dex. So it's in a scientific way, perhaps the least a substructure with least metallicity that is also kinematically coherent, right? And just to put it in perspective, C19 has a metallicity which is 2,500 times less than that of Sun. So it's a recent result. So these are the kind of things that we can do by building these computational tools such as Stream Finder, and then processing this complicated yet beautiful data set that Gaia is. But then coming back to the main question of trying to map those streams that would have been formed by the mergers, the merging galaxies. So most of the streams that I showed you previously, these were globular cluster streams, but we have also been able to map some of these streams from the merging galaxies. So these are these 3 streams: the Sagittarius stream, the Cetus stream, and the LMS1 stream. There are 3 of the broad streams of our galaxy. And they have very interesting properties. So for example, the Sagittarius, so all 3 of them are inclined almost nearly perpendicular to the disk of the galaxy. So for example, Sagittarius has an inclination of 76 degrees. So if something has an inclination of 90 degrees, that's just right on perpendicular. So Sagittarius has an inclination of 76 degrees or about. These are of course approximate values. Cetus is 60 degrees and LMS1 is 75 degrees. So they're polar, which is quite interesting in streams. Now, Sagittarius spans outer galactic halo ranging from 15 to 100 kiloparsec. Cetus spans intermediate halo ranging from 24 to 36 kiloparsec. And LMS1 spans the very inner regions of the galactic halo of about 10 to 20 kiloparsec. And because of their dynamical and to some extent also their chemical properties, we understand that the Sagittarius was only recently accreted into the Milky Way about 3 to 6 gigayears ago. And for example, LMS1 was accreted very early on, maybe 8 to 10 gigayears ago. And then we can try to imagine about reconstructing this accretion history of the Milky Way, that LMS1 must have accreted first, then perhaps Cetus fell in, and as the size and mass of the galaxy grew, then the Sagittarius merger would have accreted in, and then we can try and run these simulations and understand how the stellar halo would have been populated specifically because of these 3 massive mergers of our galaxy. So these are the sort of things that we are currently trying to do. Now that was the first part of the presentation. Now I'm moving to the second part, of using n-link in statistics to detect the mergers in the action and energy space. So the question that we are trying to address is still the same, of trying to detect and analyze mergers, but using a different technique. And so the question is that how to see these past mergers of the Milky Way that at present must be phase mixed in the position and velocity space, because that's what's happening. If you have a merger falling in, it just gets phase mixed in the galaxy. But because the actions and, for instance, energy, they're dynamically conserved quantities. So if we map these positions and velocity in this action on energy space, so these mergers will form groups, as you can see here, and then we can try and detect these groups and then say that, okay, this group is one merger, this group in second merger, and try and see how many mergers are in the galaxy and study their properties. But what traditional studies have done is that they have used the positions of stars from Gaia, for instance, and then have computed the action and energy components of those stars. And then majorly what traditional studies have done is that they have manually and visually tried to select mergers. So they've looked for overdensity, and then they say, aha, there's an overdensity, that's a merger, which is one way to go about it. In our study, what we do is that we do not, so the first new thing that we do is that we do not use stars. We use globular clusters, streams, and satellite galaxies to compute their energy and action. And then the second thing we do that instead of finding these overdensities manually, we try to implement a procedure that can statistically detect these mergers instead of making these manual selections. So I'll talk a bit about that. But the reason, but then you may ask that why are we using these globular cluster streams and satellites instead of stars? Because you can well imagine that these massive mergers, in addition to having stars inside them, they would have had globular clusters or perhaps their own population of tiny satellite galaxies each merger would have had. Then even those things then would have accreted in the galaxy, just like stars. Even these globular clusters and streams would sort of group together in the action and energy space. So this is a good way to go about it, except that it's kind of unexamined. So we thought that it'd be a nice idea to examine this. So this path, going about this path of trying to use globular cluster streams and satellite galaxies to find mergers could be an important technique, because it can help us understand the origin of these old and metal poor objects in our galaxy. How many of these objects were formed in the galaxy, how many were accreted inside mergers. It can perhaps allow us to understand the origin of metallicity floor, which has been pushed to minus 3.4 dex now because of the C19. And so you can ask that, did C19 form in the Milky Way, or did it accrete inside a merger? And also to understand the formation of globular clusters and satellite galaxies inside proto-galaxies, because if you can detect these mergers in the form of globular clusters, that's also telling us which globular clusters form inside which merger galaxy. So we can try and understand these scenarios. So now I'll walk through the procedure of detecting these mergers. Is that first of all, we created this very large catalog of these 257 halo objects, comprising of 170 globular clusters, 41 streams, and 46 satellite galaxies. So all of them have their 60 phase-based measurements based on Gaia EDR3 catalog, and these 257 objects are shown here. Then the next step is, of course, to use this 16 information and compute actions and energy and other orbital properties. So for globular clusters, those 170 objects are shown here. This is for the satellite galaxies, and this is for the streams. So just to interpret this diagram, so each cloud that you're seeing here is one globular cluster in this particular map, for example. And the reason that there's a cloud of these 1,000 points is because each object has a phase space uncertainty associated with it. So what we do is that for each object, we are not just sampling one orbit, we are sampling thousands of orbits to take into account that measured uncertainty that it has. So that basically that sampling of orbits, and basically for each object, we compute 1,000 energies and 1,000 actions, taking the uncertainty into account. That gets translated into this dispersion that we are seeing in action energy space, these crazy bananas that we are seeing. And now the idea is basically to try and find groups of objects in the space that we have, because that can be translated as mergers. So we use n-link, we couple it with a statistical procedure, and instead of making a manual or visual selection, what we do is that we use the statistical procedure, and for each object we assign a group probability by using these for each object using their 1,000 values of action and energy. So in this way, we make a 2 sigma detection. So here I'm showing you all those mergers that are detected with a significance of more than 2 sigma. And you can see that these different objects, they form links between each other. And the link is basically defining which objects form part of the same group. And then by this representation of linkage, different groups get separated, as you can see here. So this is the Sagittarius group, the Cetus group, the LMS1 group, the Gaia sausage Enceladus, the Sequoia group, and so on. We find one new merger, which is Pontus, which is just below Gaia sausage Enceladus. And in total, we find that 25% of these 257 objects belong to one of these mergers. So it shows that the statistical method that we've adopted is working. Now there's this globular cluster 1851 that belongs to Gaia sausage Enceladus, as found by us and also by previous studies. And I think Rosina will be talking a bit more about this in the next talk. Looking forward to it. Now, please note that I've already spoken about these 3 specific mergers, the Sagittarius, the Cetus, and LMS1. And it's nice that we can map these mergers in using the star information and also using just globular clusters and streams. So it's a nice way to use these complementary techniques to find mergers in the Milky Way. Now, what we can do is that we can complement this dynamical information with the metallicity and try and see how it looks like. So it's hard to see any particular trend, except that as the energy increases, the metallicity decreases, which makes sense because the objects that are created inside mergers are usually metal poor compared to those that form within the Milky Way in the disk and the bulge. Now, specifically, I would want to point about this LMS1 Wukong merger that represents the most metal poor merger of our galaxy. And that's because the 3 most metal poor streams of our galaxy, C19, Silgur, and Phoenix, they were likely accreted inside the LMS1 Wukong merger, as we find in our study. And as you can see, that the tail of LMS1 Wukong goes down to minus 3.4 dex or so. So again, this is addressing the question that I raised previously, that C19 came inside LMS1 Wukong and was unlikely to have formed in the Milky Way. So we can try address questions like these. Now there's the 7th merger that we found at low significance, but these 5 objects are grouped together in the action space, and they also have very similar stellar population, as you can see here. So we regard this as a 7th merger, but we need to analyze this in more detail. So this brings me to the summary, my last 2 slides. In the first part of the talk, I spoke about Stream Finder, which is a state-of-the-art algorithm to detect streams using Gaia dataset. Some of the highlights of these streams include the Fimbulthal stream, which is a stream of the Omega Cent cluster, C19, which is the most metal poor stream of our galaxy. Then the LMS1 stream, that is a broad, massive stream and represents the most metal poor merger of our galaxy, and it brought in the C19 stream. And we must realize that streams provide a live show of the galaxy formation process, because this is how, be it a globular cluster stream or a dwarf galaxy stream, it's just basically showing us that this is how the stellar halo formed, that a progenitor fell in and the stars began to escape the progenitor, and that's how the galaxy, the halo got formed, the stellar halo got populated. So that's how it is, and it's a nice way to think about it. Then in the second part of the talk, I spoke about this new technique to detect Milky Way mergers by using the action and energy of globular clusters, stellar streams, and satellite galaxies. So this is a paper that's been accepted, but it's still to come out. Hopefully it will come out by in the next 2 or 3 weeks. So in this case, we used Gaia EDR3 measurements of these 257 objects, and we try to implement this statistical procedure to detect mergers. Now, one of the interesting things about this procedure that we hope that it should be reproducible in cosmological simulations, such as E-mosaic simulation, Fire 2, Illustris, or Riga. Hopefully, that's still to be tested. Now, in total, we detected 7 massive mergers. The discoveries of the Pontus merger, and we also find that LMS1 Wukong represents the most metal poor merger of our galaxy. And then this global dynamical atlas of Milky Way mergers that we have found, thanks to Gaia EDR3, the Gaia dataset in general, and also with these new statistical tools, these results provide a present day reference for the galaxy formation models. So these are the kind of directions that we're currently trying to explore. So with that, I thank you very much for your attention. Thank you.
Thank you very much, Kayati, for this beautiful talk and this beautiful work.
Welcome.
The floor is open for question, and I look at the chat and then the raised hands, and I have Ricardo Chivion first.
Okay, so thank you very much for great talk, Kayati. Two questions. They're hopefully short questions. So as you know, Davide Massari and collaborators have identified mergers using globular clusters in the integrals of motion plane, just the same way as you hope, but however, adopting a different procedure to associate clusters to a given merger. Have you compared your assignments to theirs, right? And on top of that, I wonder what do you mean when you say bulge clusters? And the reason why I ask that is that the Milky Way doesn't seem to have a classical bulge, or if it has any classical bulge, it is very difficult to even detect. Therefore, associating clusters to the bulge is something that I find a bit problematic. So I wonder if you would like to comment on that.
Yep. So to answer your first question, the associations that we find are in some cases are a bit, sorry about the dogs barking in the background, are a bit different in some cases. In some of the cases of some of the mergers are different than that found by David Massari, and also by some of the other people who have also worked along the same lines. So for example, in comparison to David Massari's work in 2019, that's based on Gaia DR2, and they use only globular clusters. The Sagittarius associations are more or less similar, but for instance, they do not talk about the Cetus association at all. Gaia sausage Enceladus, in our case, it's a bit smaller group compared to Massari, but we have most of the clusters that they have, but it's a smaller group. LMS1 Wukong is again something that they don't talk about, because LMS1 Wukong didn't exist till that date. So they basically tried to associate globular clusters with the already previously known mergers. So yes, so I hope that answers the first part of your question. The second part is that galactic bulge. So by that, do you mean that the Milky Way doesn't have a bulge, but it has a bar? Do you mean
yes, yes. So therefore, the question is, do you think these clusters are formed in situ, or were they accreted?
Right. So, I mean, you're absolutely right that the only reason to, so basically, the way I understand is that these groups that we are seeing here, they were formed in situ. The reason being that they have very low energy, and the general understanding is that because they're very low energy, they are part of the deep potential well of the galaxy. So they must have formed within the Milky Way. Maybe some very ancient merger, maybe the one that occurred 12 giga years ago, must have came at the very central regions of the galaxy, and then would have brought in some of these globular clusters. That's also possible. But then I think then it's basically like saying that we are trying to peel off the shells of an onion to find the onion. The shells are the onion. So maybe it really depends what we call galaxy at 12 billion years ago. But I mean, just to answer your question, I mean, even if we call this galactic bar, so you may very well call this galactic bar instead of galactic bulge, but the idea was simply that these must have formed in the very central regions of our galaxy.
Okay, spoiler alert, next month when I talk about our findings in here in Liverpool, I'm going to talk about an accretion event that happened 12 years ago.
Oh, perfect. That's a nice circuit.
All right, we have another question by Akshara Vishwanathan. Please, go ahead.
Hi, thanks for the amazing talk. I was just wondering if you ever checked if there is a trend in the metallicities or the radial velocity dispersion of the 25% of the streams that were part of mergers versus the ones that you think are in situ.
Oh, I'm sorry. Do you mean the velocity? I mean,
if there was any trend between, if there was any trend in the metallicity or the velocity dispersion, are like are the 25% which you think are part of the mergers, are they like more poor than the other ones, or just curious to
right.
know.
Yep. So, I mean, if I understand your question correctly, so these, I mean, you can imagine a polygon that I'm trying to make with my mouse. So that's basically
Yes.
form part of the mergers. And of course, there are different mergers. So they are, I mean, you can see that they're definitely more metal poor than the things that formed in the Milky Way. So that's one. But if you also talk something about the velocity correlation between velocity dispersion and metallicity. So that's something I haven't explicitly checked. But what's the motivation of that question, if I may ask?
No, I was just curious. There are a few streams that people find these days that like the velocity dispersion show that they might be from dwarf galaxies, but the
Right.
melicities show that they might be from
Right. Yep.
the cluster. I was just wondering if there's any correlation between it coming from an accretion event or in situ.
Right. So I haven't measured I mean, for some of these streams, I've measured independent dispersion, but I mean, each object here corresponds to a one object. So this is one stream, this is one globular cluster, this is one satellite galaxy, this is one globular cluster. So I'm more thinking about the way that if there's a correlation between the velocity dispersion of a given merger and perhaps the average metallicity of that merger event. But then, I mean, you're completely right in also asking that the metallicity and a velocity dispersion of a given object. I think you're more interested in that.
Okay, the next question is by our president, Karsina.
I would like to ask, is it possible to use your method in revealing nuclei of those infallen galaxies?
You mean the nuclear, what we call as nuclear dwarf galaxy or a nuclear star cluster, I think.
No, but every galaxy has a nucleus. So if they are merged, they become streams. So is it possible to use your method in revealing what is the nucleus of the galaxy? For example, for this Gaia Enceladus galaxy, what is the nucleus?
So I mean, most of the galaxies would have had nucleus, but I mean, that's just to answer as per my understanding, just to answer the first part of the question, that I'm not sure if every galaxy has a nucleus, but most of them would have had. The procedure at present does not, I don't think there's a straightforward way to define a nucleus of a system, but I mean, we can do post-processing. So for example, if we have this particular galaxy, then we can perhaps look for some central point in the energy and action, and an object close to that center point may correspond to the nuclei. But then again, I mean, there's dynamical friction in the galaxy, and there would have been precision. The orbits would have been mixed and would have undergone at least some precision. So it will be, so taking into account the evolution of these mergers plus the evolution of the galaxy, it will be hard just based on dynamics. But of course, if you have a chemical information and you see some object has very weird or peculiar properties, complex stellar population, then you'll be more likely to call it the merger. So it's the nucleus. So it's a combination of the chemistry and the dynamics, I think.
Thank
We
you.
have another question by Ricardo.
Just one quick question that I left for the end. So, you mentioned that there were seven massive accretion events to form the halo, right? So, can you please define what you mean by massive?
Yep. So that's to put a lower limit as per our study. That's not to say that those were the only mergers, but just to put a lower limit on these on all the mergers of the galaxy. So by massive, I mean so based on these the masses of these globular clusters, we estimated the total stellar mass of the merger, and then based on the total stellar mass, we estimated the total dark matter halo mass. So I mean, almost all of these mergers have masses that have dark matter halo masses more than 10 to the 9 to 10 to the 10 solar masses, halo masses. So then it depends what threshold do you choose to call it something massive. So, but most of them have halo masses of more than around 10 to the 10 or more.
Okay, so but then you know we have a fairly reasonable constraint on the stellar mass of the halo, right? And the question is whether, because this 7 number is much larger than what we've been hearing from others, like so I wonder whether your in the end whether the total stellar mass, right, it matches the existing stellar mass of the galactic halo.
So that calculation, I mean, I understand your question of summing up this and then try to get the stellar mass of the Milky Way. So that's something that it's a good question and I need to do. But I mean, here we say 7 mergers, but I mean, I hope if you've read papers by Charlie Conroy and team who are analyzing and leading the H3 survey. So in principle, I'm regarding this group as Sequoia, Arjuna, Itoy as one group, but as per their translation, it's basically a merger made up of 3 different mergers. It's a group made up of 3 different mergers. So in reality, there are probably 9 to 10 mergers as per their study. As per my study, as per our study, it's a 7th merger. So I'm not sure why one would say that it's too many mergers. I mean, is there an expectation on the number of mergers that Milky Way should have?
I think that there's an expectation certainly on the total stellar mass of the halo, which should be not much more than a few times 10 to the 9 solar masses, according to current estimates, right? Then you take Gaia Enceladus, which is 10 to the 9 solar masses, roughly 10 to the 8.5, right? Heracles, if it indeed exists, and then you soon run out of a possible massive merger, right? So I mean, I think these numbers are still fluctuating a bit, right? So,
True.
but I think it's definitely something that we should try to understand.
The reason that these numbers are also fluctuating is because it depends what you call Gaia Enceladus. I mean, it basically depends on the selection you make in the action space, right? If this is your Gaia Enceladus, then you have more stars. If this is your Gaia Enceladus, then you have less stars. So that's also one of the reasons that the numbers are fluctuating.
Maybe we have time for one more question before we have to move on. Emma.
Yeah, hi. Thank you for the talk, Kathy. I was wondering how you kind of make the distinction between these different groups, like how you don't know to link Gaia Enceladus and Pontus, like what in the method stops you linking them together?
Right. So it's basically simple. I mean, it's not simple, it's a bit complex, but the idea is that we are using this procedure, n-link, and there's this. So basically what we are doing, then I'll have to go into the nitty-gritty of
Sorry.
No, it's perfectly fine. I mean, the paper will be out soon, so it perhaps would be easier to read it there. But just to quickly go through it, because I know we are limited by time, is that we are basically iterating over all of these points that we are seeing here, and that allows us to assign a probability value to each of these objects. And based on this probability and some contamination model that we build, we make a 2 sigma detection of these mergers. So here, these associations that I'm showing you is based on 2 sigma. So we basically try to find only those groups that have had higher sigma, so as to have a pure sample. And then in that case, I mean, this is the map we get, that these groups get separated into different objects. But that's the basically idea. I mean, of course, if you lower this detection, you make it very small, then not only Pontus and Gaia's sausage, but even Pontus and this, and then with Cetus, everything will form one big group, which is the Milky Way. So it's just to have some threshold value that's significant enough.
Okay, thank you. I look forward to reading the paper.
Okay.
Welcome.
Thank you. Thank you very much, Kiati, for for an excellent presentation.
Thank you so much for listening. Thank you.
We now have